All right, Calc, you guys all know that I'm home today. If you don't have the notes for section 3.3, I'm going to go through these with you and the homework assignment. If you don't have the homework assignment already, they are on my desk. So if you're in the library right now, I have no idea where you're at. If you're in the library right now, somebody go back to my desk in my room and get the notes and the homework assignment. I'm going to go through these notes with you. So section 3.3, evaluating limits analytically. So this is like not graphing, just looking at the equations. There are tricks that we can do to a function to make it so that we can evaluate limits even at places where we can't plug it in. Okay, so we're going to look at some basic rules for finding limits. There's 3 of them. So this first one applies to number 1. Okay, so these go together. So I'm just going to show you the example on how this works. Okay, they give us the answer. Here's the answer. This is what the answer is, but let me show you how this works. So the limit is x goes to 2 of 3. We did one like this yesterday on your 3-2 homework assignment. I think it was like -1 or something, but my function is 3, and this means y equals 3. Okay, so just like, you don't have to graph this always, but I'm just going to show you on the graph why this is consistent. Okay, y equals 3 is the line here at 3, all the way across. Okay, and we're trying to find the limit as x goes to 2. So at an x coordinate of 2, a limit is saying what should the y coordinate be. Okay, and most of the time a limit is saying what should the y coordinate be if it was there. Well, this one does, it even has a y coordinate. Like, there's nothing wrong with this function. Like most of the time we're evaluating limits at places where there's holes or vertical asymptotes. There's not even any holes here. So all we need to do is look at what the y coordinate is at 2, and the y coordinate at 2 is the same as all the y coordinates, which is 3. It's 3 going all the way across. So whenever you have a limit, it doesn't matter what this number is. It doesn't matter where you're looking at. If it's just a solid number, meaning like y is the same number going all the way across, it's just going to be that number. The limit's just going to be that constant value. Okay, there's nothing else you can do with that. Number 2 says the limit as x goes to -4 of x. Now this is y equals x. Okay, so if we're looking at the linear function, y equals x, this is like y equals x plus 0. So we start at 0 and the slope is up 1/1. This is y equals x. This is the graph of y equals x. And they're saying at an x coordinate of -4. So -1, 2, 3, 4. What is this y coordinate? Well, that's also going to be -4, right? So when you have the limit at any value of that, it's just like taking the -4 and plugging it in for x. -4 plugged in for x is just -4, because it's going to be at the same spot on the x and y, because it's the line y equals x. Okay, there's not even any holes or vertical asymptotes or anything in there, so you can just plug that -4 in. Okay, here, same thing, x squared is the function that we're looking at. So we have a parabola, and he's doing this, okay? And there's no holes, or there's no funny business, or no vertical asymptotes or anything. So you can just take these numbers and plug them in for x. Okay, if I go to 2, this dot right here is going to be 4 on the y. Like, it's going to have a y coordinate of 4, right? So 2 squared, if I plug 2 in, 2 squared is 4, and the limit is 4, all right? So whenever you have things that don't have like funny places, like we know what holes look like, where they're in the top and the bottom and they cross out, anything like that. If you don't have any vertical asymptotes, you can just plug the darn thing in, right? So that's an example of any of these. Find the limit. The first thing they want you to try to do always is to try to plug the limit in, okay? On the test, you're going to get to some problems, and you're going to be used to trying to find limits, like here, like trying to plug 1 in. Well, I can't plug 1 in there because it would end up giving me 0 on the bottom. So I have a hole or a vertical asymptote there. I cannot do that, okay? But always try to plug it in first, right? Try to plug it in first. Like 2, I can plug 2 in here. This is 4 times 2 squared plus 3. So his limit, or his where the y coordinate would be, is going to be like 16 plus 3, 19 maybe, something like that, right? That's the y coordinate, okay? Here, I have a denominator, which means I have a vertical asymptote, okay? X plus 1 means I have a vertical asymptote at x equals -1. But look at what we're plugging in. We're trying to find the limit at positive 1. We don't care about negative 1. We're trying to find the limit at positive 1. So even though this has a vertical asymptote and some weird funny business, we can still plug this thing in. It's still legal. So I have 1 squared plus 1 plus 2. That's going to give me like 4 on the top over 1 plus 1 on the bottom. So that gives me an overall total y coordinate of 2, or the limit is going to be 2. Okay. In this one, again, we can just plug the number in. So 0 squared plus 4 is the square root of 4, which is just 2 again. Okay. This one, try to plug it in. 3 squared is 9 times 2 is 18 minus 10 is the cubic root of 8, which is 2. That's a lot of 2's. I don't know how we came out with a lot of 2's. Anyway, so always just try to plug the thing in to start with. Here, like going forward, we're going to learn like what you do when there's funky business happen, but always try to start with, always try to plug your limit in. Okay. All right. Now these ones, this example is functions that, you can't plug in, like, 1 goes here. Okay. And if 1 goes there, you end up with 0 on the bottom, and we can't have that. That's bad. Okay. So what's actually happening here is that x minus 1 is a whole. But what we're going to do is we're going to use some division. We're going to divide these, get rid of the whole, and then we are allowed to plug 1 in. And I'll show you kind of how that works. Okay, that kind of maybe seemed confusing. So this top one is x cubed minus 1. So we can either use long or synthetic division, I guess, if we want to, because we're dividing by x minus 1. So let's do some synthetic division. Sure. Let's do, when we write this out, though, we have to insert our zeros in. So this is 0x squared plus 0x minus 1. That's what he will look like, okay? So for synthetic division, we have 1, 0, 0, negative 1. And we are dividing out. If we set this equal to 0, this will be positive 1, okay? So I drop the 1 down, multiply by 1, 1, 1, 1, 1, 0. Okay, so this is the function that I have left over. Okay, and so if I put my x's back in, we find that this is x squared plus x plus 1. So what happens is when I have this function here, if I divide it out, it actually ends up coming out to be like that. So this will end up giving me the function without the whole. It like basically gets rid of that whole for me, and I don't have him anymore. So evaluating this limit is the same as evaluating this limit. Okay. You might wonder why on my computer, most of the time limits, when you write out limits, the limit as x goes to 1, like goes underneath of the limit. But for some reason, when I type this out, my computer puts it off to the side a little ways. So if you're ever wondering why I'm writing it underneath, that's why I'm writing it underneath, is because normally it is underneath, but my computer for some reason doesn't write it underneath. So evaluating this limit is the same thing as evaluating this limit. And now that I've gotten rid of the whole in there, I can just plug 1 in to that function. Okay, so we can use some division to divide it out. You might have to use long division instead of synthetic like we did here, but you should just be able to use division to divide it out in some cases. And if I plug those in, I should get a y coordinate or a limit of 3. Okay, so that's one strategy. Strategy number 1, divide, either using long division or synthetic division. That's strategy number 1, is we're going to divide. Okay, actually, this is strategy number 2. Strategy number 1 is try plugging the thing in to begin with. Try plugging in. That's what you're going to try first, okay? So the first thing you're going to do is you're going to try plugging it in. Second thing you're going to do is try dividing them out if you can, okay? Third thing is this is something called strategy for finding limits. This is like the steps that we're going through. Learn to recognize which limits can be evaluated by direct substitution. That was our number 1. Okay. If the limit blah 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 cannot be evaluated, try to find a function that agrees with f for all functions other than blah blah blah. That just means try to divide and see if you can get a new function. Okay, so that's strategy number 2. Strategy number 3 is apply theorem 3, 6, whatever, to conclude analytically that blah blah blah. Okay. So let's go down here. This is kind of like strategy number 3. Strategy number 3 is to factor, I say, or dividing out and rationalizing techniques. So this is a factoring one, okay? So if I look at this, I'm trying to find the limit as x goes to -3. If I try to plug -3 in there, I end up with 0 on the bottom. We can't have that. So you could use division and divide this out, or I recognize that this top guy right here is a simple trinomial, and I can factor him down into x plus 3 and x minus 2. And when I do that, the x plus 3's cancel out, okay? So evaluating this whole limit is the same as evaluating the limit as x goes to -3 of just x minus 2, because I've gotten rid of the things that cancel out. I've like removed the whole out of the function, okay? So all I'm going to do is take -3 now, and now I can plug it into there, and my limit is going to be -5, okay? So that's your second or third technique, is try to factor it down, which is kind of similar to dividing, like without actually having to divide. You're canceling things out, you're dividing it out. And then plug your limit into that, okay? Now this last technique, number 4, is called rationalizing. Okay, and we've done rationalizing before when we have like square roots in the denominator, but this is rationalizing what the numerator actually. Mallory, we did this problem in trig the other day, and I said, Mallory, we're going to do this in limits. We're going to find this in limits. This was the problem that I was bothering you about, okay? So we're going to rationalize the numerator here instead, and I'm going to show you some tricks to how this will always come out, okay? So we have this stuff going on here, all right? We're going to rationalize the numerator, which means we have to multiply by the conjugate of the numerator. Normally we're rationalizing the denominator. Now we're going to do the numerator, and we're going to multiply by the conjugate. The conjugate of that is the square root of x plus 1 plus 1. Okay, so we're just changing that sign. That's the only thing that we change. And if we multiply it by the top, we have to also multiply it by the bottom. Okay, so we're multiplying by the conjugate of the top, and doing that to the bottom as well. And what we're going to do is we're going to FOIL this, okay? It's going to come out really, really nice. Even though the middle steps might look ugly, it's going to come out really nice. So we're going to start with the square root of x plus 1 times the square root of x plus 1, which is just x plus 1. It's like the inside stuff falls out, okay? Then we do the square root of x plus 1 times 1, which is just the square root of x plus 1. Then we have the inside pieces, which is -1 times the square root of x plus 1, which is negative square root of x plus 1. And you can see already that these two are going to cancel. And then the last thing is -1 times 1, which is -1. That's my whole top stuff, okay? On the bottom, don't ever FOIL the bottom out. Don't do that. Just do this. Leave the x here. And then it's like we're cheating. We're just like writing them together. We're not even multiplying them out, because I'm going to show you what happens, okay? So this plus 1, that minus 1 cancels in addition to these two canceling. So all we have left on the top is x, and on the bottom we have this stuff. But we have an x on the bottom here, and those two can cancel. So we have nothing left on the top, which means we just have a 1. And on the bottom we have x plus 1 plus 1. That's what we have on the bottom. Okay, now we were originally wanting to evaluate this limit. Oh, I didn't go through. We can't evaluate the limit at 0, because if I try plugging 0 in, I end up with 0 in the denominator. But now that I've done all that rationalizing stuff, evaluating this limit is the same as evaluating the limit as x goes to 0 of this stuff, right? I've just changed what he looks like, right? I didn't change him at all. I just changed what he looks like. So now I can plug 0 in, okay? And I have the square root of 0 plus 1, which is the square root of 1, and the square root of 1 is 1. So I have 1 over 1 plus 1, which is 2. So the limit here is going to be 1/2. That's what he will look like, okay? So that is the fourth technique. That is the rationalizing technique, okay? So you should be able to, on your homework assignment, if you can't just plug it in already, you should be able to do one of those other 3 things to figure out and evaluate the limits. And if you need to go back through this video and watch that again, you sure can. We're going to skip the squeeze theorem. Maybe I'll talk about that when we're together, but it's kind of one that you kind of have to I have to be there to talk about. So using one of those 4 techniques, that should get you through the majority of the homework assignment. Okay? I'll see you next week.